Hi, my name is Jake Evanson, and this is my Everyday Physics video assignment. My topic is all about understanding the difference between instantaneous and average velocity and how to solve for them. I will be using a mixture of diagrams, calculations, graphs, and also a real-life demonstration to prove my points. I will also outline some real-world applications of these topics. Also, for extra content, I will be going over angular velocity and the real-world applications. Let's get started. Starting off with average velocity. So the definition of average velocity is the change in displacement over time. And an important thing to note about this is it tells us nothing about the velocity at specific points in time. Let me show you an example. So say we have a turtle who is moving east on this plane. All right, he displaces 5 meters in a time of 10 seconds. So we take the formula for velocity, which is velocity is equal to displacement over time, and then we get velocity equals 5 meters over 10 seconds, and that's 0.5 meters per second. So we would say that the turtle's average velocity was 0.5 meters per second to the east. But an important thing to note is that it could have been going 0.5 meters per second the entire time, or it could have been going fast at the start, slow at the end, or any combination, so long as it traveled 5 meters in 10 seconds. We don't know anything about the speed at individual points in time. Instantaneous velocity. So the definition of instantaneous velocity is the velocity of an object at a specific moment in time. So this is different from average velocity, as it shows the exact velocity at one moment in time, an infinitesimally small moment in time. So you could say that as delta t approaches 0, this value gets more accurate. So the time that changes in between starting the measurement and ending the measurement, as it gets closer and closer to 0, you get a more accurate reading of the instantaneous velocity. So let's have a look at an example. So we have a car that's moving forward to the east, and we're not given velocities at all. We're only given the times and the distances that it's traveled at each times. So at 1 second, it's displaced 1 meter. At 2 seconds, it's displaced 4 meters. 3 seconds, it's displaced 9 meters. At 4 seconds, it's displaced 16 meters, and so on. So we could say that this car is accelerating, and we know that because the change in time is always 1 second, but the delta d is getting greater every time. So if you're covering more distance in the same amount of time, that means that you're accelerating. In order to solve this, we can use calculus and using limits and things like that, or we can also get an approximate value using a graph. And I'll show you how to do that right now. So this is a position versus time graph for the motion of the car that we just looked at. So we have displacement in meters on the y-axis and then time in seconds on the x-axis. And then we just plotted the points that we were given. So at time, after 1 second, it was displaced 1 meter. After 2 seconds, it was displaced 4 meters, and so on. So we want to solve for the instantaneous velocity at 3 seconds. So at the instant that 3 seconds has gone by, what was the velocity of this car? So what we would do is draw a tangent line to this curve, which is a straight line that is only meant to touch at this point on the graph. So as close as you can, you just want to kiss that curve. So then once you have your line drawn, you would want to take the slope of that line. That would give you an approximation of the instantaneous velocity of that point. So I drew a line already, and I found that the rise was displacement of 16 meters, and the run was 2.75 seconds. So then you'd want to do the math for this graph. So you take the So formula velocity is equal to displacement over time, and then plug in our values of 16 meters and 2.75 seconds, and then you get approximately 5.8 meters per second was the instantaneous velocity after this car had been driving for 3 seconds. Let's have a real-life demonstration on how a speed gun measures instantaneous velocity. So it works on a concept called the Doppler effect, which is the waves coming from a moving object would be compressed in front of it and extended behind it. So what the gun does is it shoots a radar with a known frequency, and when it receives back, it can determine the instantaneous velocity of that object. So if it receives a higher frequency, it can determine what the speed of that car is, and it also knows that the car is going towards the gun. And if it receives a lower frequency, then it knows that the car is moving away and can calculate the velocity of that car based on the frequency of that wave that bounces back off the car and hits the gun again. So if a radar was over here, the gun was over here, and the car was here, it would look something like this. So now let's have a look at angular velocity. So angular velocity is how fast an object rotates relative to another point. And some things to note are that we use radians when doing these calculations rather than degrees. So instead of 360 degrees being all the way around a circle, it is actually 2 pi radians is how far one rotation is. And angular velocity is the change in angular rotation over time. So we get our formula is we get angular velocity represented by omega is equal to delta theta, which is measured in radians, over time. And we can also say that omega is equal to 2 pi times the frequency, which makes sense because 2 pi is how far is one rotation is on the circle, and frequency is how many times that object rotates per second. So we get the speed in radians per second. So, and how do we get linear velocity from angular velocity? So what we would do is we would say that the linear velocity v is equal to 2 pi times r times frequency, which is the circumference of the circle, 2 pi r, times how many times it goes around per second. So that would be the linear velocity of it. Or we could say that velocity is equal to omega r, and omega is just 2 pi f and then times r, which makes sense. Now for some real-world application of these concepts that we just learned. So the problem that we're given is you're an engineer working at a theme park, and you know that the wheels on a roller coaster need to be greased every 50 kilometers. The wheels are 0.2 meters in diameter and rotate 10 times per second. How long will it take for the wheels to need grease again? So we take our formula, omega is equal to 2 pi f, so angular velocity is 2 pi f, plug in 10 hertz, which is 10 times per second, and then we get 62.83 radians per second is the angular velocity of these wheels. And now we want to convert that into linear velocity. So we say linear velocity is equal to omega r, so angular velocity times the radius. So we get the radius of 0.1, plug that in, and then we get a linear velocity of these wheels is approximately 6.3 meters per second. And then we plug in our formula, velocity is equal to displacement over time. So we get our displacement of 50,000 meters, 50 kilometers, and then divide that by our linear velocity, and we come up with, after converting seconds into hours, we get 2.21 approximately hours before these wheels need grease again. So we can say that the wheels need to be greased every 2.21 hours of roller coaster runtime. So this is actually useful in the real world, and this might be a calculation that an engineer would do at a theme park. That concludes my presentation. You should now know the difference between instantaneous velocity and average velocity. You should now know angular velocity and also real-world applications of these concepts. Thank you. Goodbye.